Hello my friends, let me show you the problem 2 in EGMO 2021. This is Webpeak. Don't forget to subscribe if you want to learn more on Math Olympiad. The problem is a functional equation. We need to find all functions from Q to Q such that f of y plus xfx equals f of y plus x squared. And this needs to be true for any rational number x and y. If you want to think about the problem, pause the video here. The solution is coming right away. Since the domain of the function are rational numbers, we are looking for an additive structure on the function f. A funny fact is that we are not able to identify any special value of this equation. For example, plugging 0 at x gives us a tautology. Plugging x equals 1 does not lead to anything particular neither. Nevertheless, we can ask a converse question. Can any other number a take the value 0? And the answer is no. Indeed, if f of a is 0, then a times f of a is 0 as well. So the left-hand side of the equation is f of y, but the right-hand side is f of y plus a squared. And obviously they do not match each other if a is different from 0. So f of a cannot take the value 0 when a is not. Now let's use capital A to denote a times f of a. Then the equation tells us f of y plus capital A equals f of y plus a squared. So we have this additive structure, and by induction, we can prove that f of y plus n times capital A is f of y plus n times a squared. And this will be the main equation that we are going to work on. The idea is to apply this equation on another number b. Let's say b equals 1, so capital B is just f of 1. Then we have f of y plus m capital B equals f of y plus mb squared. Now if we compare the left-hand side of the blue equation and the left-hand side of the red equation, it would be really great if n times capital A match with m times capital B. And indeed, this is possible, because capital A and capital B are non-zero rationals, so a over b is again a rational number, which can be written in a canonical representation, capital M over capital N. Now, on one hand, f of y plus na is f of y plus na squared. On the other hand, with na equals mb, it also equals to f of y plus mb squared. So the constants need to match each other. Therefore, a squared over b squared equals m over n, which is capital A over capital B. And by definition, this is AFA over BFB. Knowing that b equals 1, simplify the equation tells us f of a equals a times f of 1. And this is true for any non-zero number a. Finally, it remains to determine f of 1 and f of 0. To determine f of 1, we take x equals 1 and y equals f of 1 in the original equation. We get f of 2 times f1 equals f of f1 plus 1. Now remind that f of 1 is non-zero, so we can apply the linear form, and we get f of f1 equals f1 squared. F of 2 times f1 is 2 times f1 squared. And this implies that f1 squared equals 1, so f of 1 could only be plus or minus 1. Finally, we still need to figure out the value at 0, so let's take x equals 1 and y equals to 0. We get f of f1 equals f of 0 plus 1. Now since f of f1 is f1 squared, which is 1, so necessarily f of 0 equals 0. This means there are two solutions, f of x equals x or fx equals minus x. The funny thing in this proof is that we first derived the linear form before knowing the value as 0 or 1, which is kind of unusual. Now we can also ask the question, what happens if the functional value live in the space of real numbers instead of rational numbers? The answer will be the same, but the proof is substantially harder than the one we have here. If you are interested, give it a try. Hope you enjoy the solution. See you next time. Bye bye.